everyone. Very nice to see you here today. I'm going to talk about learning the right thing with visual attributes. This is work done with a few of my students, Chaoye Chen, Aaron Yu, and Dinesh Jayaraman. So to set the stage, the kind of problem space we're interested in is moving beyond image labels. So you can ask, what does it mean to understand an image? And that I don't think we can at least, consistently all agree upon, but we can probably agree on that it's going beyond tagging objects in those images. And so here, this tagging problem of being able to categorize objects is something that, as we've seen all week, is the community's gotten quite good at, and at least making extreme progress in last years. But if we think about what we really want to know about images, it of course goes beyond this. And so, for example, it might mean understanding the story of the scene, so how a human would describe what they see. And one important part of that kind of story is not just naming the things that are there, but using very descriptive terms about them. And so these would be, say, the adjectives about the objects that are in view, or the so-called visual attributes. Things like, not knowing just that we see cow, tree, and grass, but this is a lone cow, and it's in a bright green pasture, and maybe this tree is an old tree, and so on. Okay, so we're interested then in learning how to find these attributes and name them. And the space of visual attributes, well, it's seen a resurgence of work in recent years, and again, an attribute is an adjective of the visual recognition world. It could be anything from a property describing the material or the appearance of the object. It could be something about its function or affordance. It could be the name of a part. And the key thing is these are semantic properties that are shared often across objects. So, the horse can be brown and so can the shoes. So this is something that transcends the boundaries of the object categories themselves. And these attributes are both human nameable and understandable, and if we do well, also machine detectable. So what does that mean in the context of this workshop? Well, that means there's a communication there between the human understander or user of the images as well as the machine who's trying to process them. There's some language that can connect the two. Okay, so this gives us, attributes give us a starting point to move beyond categorization towards description in language. And I first want to motivate further with some applications of what you can do once you have this, once you have some kind of communication channel built on attributes between the human and the system. For one, people are looking at ways you can perform search, and specifically person search. So being able to describe a face in order to find the face you're thinking of, or describe a person. And here's an example from some recent work doing just that, searching for a person based on these high-level properties that you want to find in a bunch of ad hoc photos. We've also been looking at interactive search. So if you want to refine your image retrieval results, you don't want to just click on things and say they look good or bad. You'd like to really just tell the system what you want. So in attributes, you could say things like, well, this is almost what I'm looking for, but it needs to be more ornate. And this is the Whittle search system from Adriana Kovashka. Okay, you can also, as people have shown, look at interactive ways to recognize fine-grained content, things that only experts might easily be able to recognize, but humans can intervene with the machine to help deduce the right label. So this is the example from the Visipedia project, looking at if the system and the human work together, they can figure out what the species of the bird is, even though the human might only be able to name attributes like the shape of the beak or the color of the back and so on. And as a final application, I'm quite interested in how attributes can help serve new ways to do supervision. So again, moving beyond images and their labels towards ways to describe and teach to a system with language. So we know the case of zero-shot learning has a lot of interest where even before seeing image exemplars in the very extreme, we might be able to teach the system what something looks like. So say a band-tailed pigeon has certain attributes and not others. Or even in a relative sense, saying, say, a mule has shorter legs than a donkey or shorter tails than horses. Okay. And you can also think of teaching beyond the zero-shot sense, even kind of enriching the labels that we give. So instead of just saying that someone's hot or not, you could also be describing what are the properties. And so people, including work from my group, have looked at how do you deepen those labels so that you're not just assigning a label to a data point, but you're really enriching it with why the label exists. Okay, so for all these examples I've given you, the thing I want you to notice is how important it is that when I say an attribute name, the machine or the system understands the visual content that I associate with that name. Now, it's very important to get that association right. Problem is, with attributes, it's easy to learn the wrong thing. And in fact, I would claim it's easier to learn the wrong thing with attributes than it is with object categories. And why is that? Well, here's some issues. One, there are plenty of incidental correlations. Okay, so particularly since we care about attributes that transcend object boundaries, category boundaries, then we might learn about attributes in a space where they're heavily correlated with one another for certain objects. But now if we start worrying about other objects where those attributes exist, those correlation patterns may be broken. Okay, so it's dangerous, in other words, to try and latch on to these incidental correlations between co-occurring attributes. Second problem, they're spatially overlapping. So at least with objects, we have some object occupying a certain set of pixels in the image. Now with attributes, we can easily have multiple attributes, overlaid, right, in the same set of spatial pixels. So something can be flat and also shiny and also red, right? So these things co-occur even in space. Furthermore, there's subtle visual differences. We see this with objects as well, but when we think about attribute and attribute comparisons, making the distinctions and having them align precisely with our language that we associate with those distinctions is challenging. They're partially category dependent, as we'll see in just a bit. And there's also variance in human perceived definitions. And again, this is where language plays an important role. We have certain held notions of what these properties are, and it actually could vary among us as well. So we want the system to understand what we mean when we say fluffy or shiny. Okay, so this is the problem. It's easy to learn the wrong thing, and yet the applications I just mentioned a moment ago really demand that we learn the right thing. Okay, so what is our goal? Well, let's learn the right thing. And we have to think about what that means. Okay, so I'm going to break out 3 different components towards this goal that we're looking at. And the first one is, how do we decorrelate the attributes that co-occur? Second one is, can we question whether attributes really are class independent? And the third one is, how do we detect fine-grained differences? Okay, so let's look first at this decorrelation issue. So first, put yourself in the shoes of a machine learning algorithm doing a standard kind of visual recognition pipeline where you're given positive and negative training exemplars and you need to learn the visual concept. And say, now you're the system, we give you these positives, these all have it, the negatives, these all don't. Okay, so this is familiar for our state-of-the-art object learning pipelines, and probably we could do a reasonable job of learning the cat category from such exemplars, right? But now consider this task. You're given these positives and these negatives. And what is the visual concept that'll be learned? Furry, green, under a tree, any of the above, right? So this is not as well defined, and you can see that once you think about trying to pose an attribute learning problem because of this visual, or the co-occurrence of the attributes, it's very dangerous in kind of blurring what you actually learn, learning co-occurring properties, learning some combination of these properties. So this is a very challenging learning task. So what's going to happen in this case, say, is maybe the system will latch on to the fact that the consistent visual thing is, green vegetation in the top right of the image. And so that texture becomes the learned signal for forest animal, but it also becomes the learned signal for brown, because at least in this kind of toy training set, there's no way to pull those two apart. Okay, so how can we overcome this problem of learning the wrong thing? Well, here's the main idea. We'd like to, instead of encouraging the system to share its features between these different attributes that it can learn, we want it to resist the urge to share. And in fact, we're going to make the system, the algorithm, compete for visual features between the different attributes. Okay, so between attributes like these, given the training examples, we want to insist that it actually select disjoint features in order to recognize each of these concepts. So that's the main insight that we have to try and help this cursive correlation. And this might allow us then, to associate green vegetation on the top for learning forest animal, but associate some color pixel properties for learning the brown property. Okay. Now we don't want everything to not share. And in fact, we'll allow some sharing, and the kind of sharing we would, as a prior, like to allow is sharing between semantically related properties. So supposing you have some external knowledge, and this can be pretty loose, it can be overlapping, but in the form of groups of kind of attributes that are related, like you see here, then we'll have a preference to allow sharing between things that are related. So in other words, say attributes within the color attribute family are likely to use similar features, that's okay, or attributes within the scene habitats could use similar features, that's okay. But now we'll combine that kind of allowed sharing or preferred sharing with our preference to compete for features. and put this together in a multitask kind of learning framework. So I'll just try to give you an intuition for how this works. Suppose we're learning some linear classifiers where we have some feature vectors for our images x, learned feature weights, which are these classifiers w, and we're learning binary attribute labels y. Then think about not just having one of these attributes that you're training at a time, but you're training all of them jointly. So now we have this matrix of the classifier parameters. Each column is a classifier, and the rows denote feature dimensions for all the classifiers. So here you see the names of attributes at the bottom. Each one is a learned classifier. So typically in multi-class learning, you actually promote sharing. This is a standard approach. You think, well, I'm going to learn all these tasks together, and I'm going to have them share parameters. So there'll be some kind of a joint learning process where these classifiers are related. And one way to do that is to penalize the L2 norms on the rows. So in other words, if these colored entries are the non-zero feature entries, these are weight vectors, remember? So these are some non-zero weights that are learned. If you want to encourage sharing, you would try to concentrate the mass within or use the same feature over and over again for each classifier. Of course, this is not what we want. We're trying to make these things compete for features in combination with semantic sharing. So here's what we do. We've split the attributes into those semantic groups. And what we'll say is that we would allow sharing within a group. So all the motion attributes are encouraged to share. And similarly, all the next groups are encouraged to share. Okay, so all our color attributes, say, all our texture attributes. And now consider the collapsed weight matrix coming from these three groups. So now I have a column for each group. Now the competition part of the feature selection will penalize the L1 norms on each of these rows. So in other words, the ideal situation is one of these groups gets to use the feature, but only one. So we'd like these to be sparse in each of the rows. Okay. So it's a structured sparsity approach to try and encode this idea of competing for features such that you don't mistakenly latch on to these incidental correlations. Okay, and the effect it has, to contrast it with other kind of regularization you might do, well, if you were to do a sparsity regularizer on the classifiers you're learning, you get a weight matrix that looks like this. This is just the W now in black and white form. White means it's on, black means it's off. And so you see there's some sparse features selected, but there's no kind of joint training between the attributes, and the problem we saw at the beginning is going to persist. Similarly, if we do traditional multitask feature learning, we'll allow features to be shared across all attributes, and the same problem is there. But once we have this notion of both competition and sharing among features, we get a feature matrix, weight matrix that looks like this, where within the group we're allowed to share, across the groups we tend not to. And that'll allow us to disentangle these attributes. Okay? So we've tested this on a number of state-of-the-art or benchmark data sets for attribute detection. And we're finding very consistent gains, right? So here I'm showing you a bunch of techniques. One's the status quo of just learning each attribute independently. This is really what 98% of methods today would do. That just happens? Okay. It's not a fire alarm? Yeah, okay. And as well as some standard feature selection or even existing ways to try and decorrelate. So we're seeing some very strong gains. We can generalize better, especially to novel unseen categories. Okay. I feel like I won a prize or something. Someone won a prize. Okay, so let's look qualitatively at some of the success cases. So attributes that we can detect correctly are shown here, and these are ones where your standard techniques would fail on these images. And it's kind of neat because, for example, look at this building where if you, like most techniques, were to latch on to the standard correlations of attributes, well, buildings tend to be boxy. So as soon as you see a building feature in a new image, you're inclined to call it boxy, even though this one happens to have a triangular top and it's not. And similarly, the zebra, zebras often have ears visible. This one doesn't. And we're able to properly say so. We also have failure cases, and here are some that we get wrong. Here we don't think there's a feather, and had we paid more attention to correlations and kind of the context of the attribute, we would get it right. So here you're giving something up by being less willing to exploit those correlations. But we think this is valuable once you want to generalize to unseen categories with attribute detection. Okay, and this also helps us more properly localize the attributes. Okay, so we've seen one way that we can try to learn the right thing. The second one I want to overview is to think about attributes as not purely class-independent entities. So what does that mean? Well, as I said, attributes one of their big attraction for us is the fact that they do transcend different object categories, right? So different things can be fluffy. And that sounds like a good, compact way to learn properties that are going to be quite powerful. But the truth is, and I think this kind of image contrast suggests for us why, well, we might go too far if we really assume that attributes can be learned in a category-independent way, right? Is fluffiness on a dog really equal to fluffiness on a towel, such that, like existing techniques do today, you could pool all training examples of anything you've seen that's fluffy and learn a fluffy model? Okay, that sounds very lighthearted, right? A serious fluffy model. So we think no, and these kind of images suggest why, that you really might need to go the other way and think about category-specific attributes. So the intuitive solution would be, let's learn category-specific attributes. You give me fluffy dogs, non-fluffy dogs, I'll learn a classifier. That's my dog fluffiness attribute. And then go ahead and give me fluffy towels, non-fluffy towels, I'll learn a towel fluffy attribute. But this sounds terrible, and this not only does it kind of discard the fact that there really is semantic connections between fluffiness and different categories, but it's also completely impractical for training. Why? Well, now you need training examples of every possible attribute-object pairing that you want to learn. That's not just a labeling cost, it's also a data availability problem. I don't know how many images of fluffy XYZ you're going to find for every possible object category. So there's some problem there. And in fact, if you look at the largest attribute labeled data sets today, ImageNet and Sun, they're rather sparse when you look at the combinations of which categories of objects have which attributes with labeled images. So probably about 25% of them even exist in these large data sets. Okay, so we won't do category-specific attributes, but the intuition of our idea is let's achieve category-specific attributes, but by transfer. So let's try to learn analogous attributes. Having seen some that are category-specific, let's try to transfer those to other categories. So what does that mean? Well, given a sparse set of category-specific models, we'll infer what are so-called, well, in this case, missing classifiers. So imagine this picture. You've got some number of object categories, and you have some number of attributes. Okay? And for any combination of those pairings that you do have data, you can train a discriminative model. So we'll learn spotted dogs, we'll learn about spotted dogs or brown dogs, and so on. Okay? But for any of these that are missing, for which, say, we have no or insufficient training examples, the idea will be to transfer between the ones that we've seen explicitly towards those other ones we have never seen. So that now I could actually infer a classifier for an attribute-object pairing that I've never seen. And so, if I've never seen a striped dog, I could still have a specialized striped dog classifier that I transfer from these other models. Okay, so that's the whole goal, and I can tell you in one slide how we achieve this. We're taking a tensor completion approach, and this tensor is going to be constructed over classifier parameters. So again, still indexing now by the object categories and the attributes. We're going to build this tensor, which is just stacking up the classifiers that we can explicitly train. So each of these tubes is a set of weight parameters for a linear classifier for the models that we could explicitly train. And then we're going to use this structure in this kind of 2D label space of categories and attributes to infer the missing entries. And so if you're, so we're performing a tensor completion, and we use an existing probabilistic formulation to do this. But the key thing to note here is that what we're inferring are classifier parameters. So this is a form of transfer learning where we're mapping from classifiers we've seen before to infer or fill in the blanks on the classifiers we haven't seen before. And there's a few things I want to note about this formulation. One, the novelty of doing transfer in a 2D label space. Right? So the 2D label space here are the objects and their attributes. Two is we like that we don't have to specify which of these attributes or object categories transfer to which. Right? So it's always a challenge in transfer learning to know when's transfer going to succeed and which things should I try to allow transfer to occur between. So here this is going to be just part of the one-step solution here. And third, I should mention, although I'm showing this all with the linear case, we can do this in a nonlinear classifier case as well. So that, in a nutshell, is the method to try and learn analogous attributes. Let me share some results with you. These are on the two data sets I mentioned before, ImageNet and Sun. And these are the largest in terms of attribute labeled data. And so we're going to be able to have labels for about 1,500 object attribute pairs here and about 6,000 of them here. Okay, and if you consider all possible combinations, that's learning, we ultimately would have 26,000 many object attribute pairings. So let's look at the results first if you were to do the standard thing that most of us would do today off the shelf, which is independently train the attributes, pull all the images from all categories when learning each attribute, and train a universal model. So here's the accuracy you can achieve if you do that on these data sets. Now let's see what you get, what kind of improvement you can get if you make these attributes category specific. And again, keep in mind, you can only do this today, or without this technique, if you have the available data for it. So for some 25% of these possible pairings. And indeed, that makes a nice improvement in the kind of attribute accuracy you can get. Okay, so specializing the attribute models helps, but it's not scalable. And so where our method comes in, you can think of this as kind of the upper bound of what we could achieve, these red bars. And in fact, the category-sensitive models are improving over the status quo 76% of the time for these thousands of attribute pairings. But what you can do now is actually extend this not just to those for which you have training data, but to all the possible attribute pairings. And that's what we're getting here in green. And we're coming quite close to this upper bound of the case where we actually had the explicit training data to work with. Okay, so we're inferring all the missing classifiers, some 18,000 of them. And if you think about what that means in savings, well, concretely, it means there's about 350K images that we'd never need to label, and yet we can still get these classifier models for. And depending what you pay your Mechanical Turk workers, that might end up to be some, well, $17,000. But it's really not just the money. Like I said in the beginning, there's data availability issues when you think about what all possible object pairings you can locate images for. Okay, so what attributes are analogous? Let's just look at a couple examples. So where are we seeing this transfer occur? Well, here's some object category, a bottle. And here are the neighboring object categories in the latent space we learned when doing that tensor factorization. And so here are the 4 nearest object categories we discover. And for those categories, I'm writing in words the attribute classifiers that we can compute are most similar to that query classifier's attributes. So in other words, when you want to learn about grayness and smoothness and roughness, say, for this category, there's some transfer that can happen between these two. Okay. And keep in mind, we're not even giving the algorithm any information about semantic relationships. It's discovering it through all the structure in these object attribute label spaces. Okay. All right, so the final thing I wanted to describe is about detecting fine-grained attribute differences. Okay. So what is a fine-grained attribute difference? Well, here's a coarse attribute difference, and this is what we're largely used to working with in the past. So you could say, the attribute is comfortable. Which of these two is more comfortable? And the men in the room can pretend not to know. No, they can tell too. This is a coarse-grained one. But here, the system could try and predict which one is more comfortable and do it with today's techniques quite well, because these images are quite different. But what about the question here? These are two images that are a lot more visually similar, and we still care about the subtleties of the visual difference. Okay? So there's a fine-grained attribute comparison problem. We want to know which is more comfortable, or which is one more formal, et cetera. And we need to do this even when the objects themselves look quite similar. So this is another challenge in learning the right thing for attributes. So let me talk about how we can do this. And in terms of doing the comparisons, well, and now we need to think not in terms of classifiers, but in terms of ranking functions. And so we've done some work in the past for developing relative attributes, which are ranking functions that capture these ordered properties among an attribute. So you train a relative attribute ranker by giving it paired training data saying this one has it more than this, so smiling more than her, smiling more than him, and so on. So once you have such training pairs, then you can learn a ranking function, say in some image, say this is some 2D image feature space, then we're going to learn some axis along which we could project all the data, and these ordering relationships are preserved. Okay, and there's a lot of machine learning techniques to do this for learning to rank, but this will give us a way to then predict for new examples where on the spectrum of smilingness does this new image lie. Okay, and that allows you to go beyond categorical attributes like not bright, smiling, not natural, to really understand the spectrum of attributes and how they compare. So with these rankers, you can situate something along this spectrum. But again, the problem is you can do it well with these global models for coarse-grained comparisons, but not so well for fine-grained ones. Okay, so here's the idea to help us learn fine-grained models for relative attributes. We're going to take a lazy local learning approach. So lazy just means that we'll delay training effort until we actually have a test case in hand, and we'll tailor the model to that test case. So we're going to train a model on the fly as a function of what we actually see as the test case. And we're going to use a local learning approach, which means that rather than use all the training data to fit this model, we're going to use data that's most relevant to the test case we have in hand. Okay, so for this ranking problem, that means your test input is a pair, and maybe the question is, which is more sporty? And we want to find those pairs that are in some way analogous to our test pair, or close, so that we can focus the learning of this ranking function on those that are really valuable or relevant for this test pair. Okay. So let me just briefly overview what that model looks like. Let's contrast this with what we would traditionally do, which is to learn a global ranking function. So again, all the training instances are pairs of data saying that A has it more than B. And if you were to learn a linear ranking function from data like this, in this cartoon, intuitively, for some test pair here, asking about the comparison with these two, it's going to be kind of overwhelmed by the distribution of very different kind of training pairs and learn the common denominator that just lays out that global spectrum but doesn't get so well the fine-grained differences. And indeed, that's exactly what we see happening in practice and what motivated this work. Instead, if you take this local approach, we're able to kind of zero in on those pairs in the training set. These green ones are labeled pairs that are analogous to our test pair and fit a model only on those. Okay. So to try and test this fine-grained attribute comparison problem, we really needed some new data. We needed some high-quality, fine-grained visual comparisons. And so my student Erin Yu led this effort to collect this Zappos 50K data set that's available now. And you can look at this as a test bed for attributes in general and specifically for fine-grained attribute prediction. So how do we know when we have fine-grained ground truth? Here's what we did. We did a two-stage annotation process. The first time, we let workers on Mechanical Turk claim that a pair was equal in an attribute strength, or more or less. Okay, so we left equal as an option. Then we gathered up all those that people said were equal, and we forced the next round of workers to really make the distinction. Okay, and then among those that were reliably answered, we took those. So we now know which pairs are subtle but answerable in a consistent way by human annotators, and that gives us a fine-grained test bed. And with this data set and others, including faces and the outdoor scene recognition data set, we're seeing very nice, consistent results where the local model shown in the bottom row is better than what you would do with the original relative attributes work, which is a global model, or nonlinear relative attribute ranking methods. Okay. And the final thing I'll share with you is the most recent step we've taken here, which is to think not only of learning a local model, but learning how to predict what neighborhood of examples is going to be useful. Okay, so in local learning, the standard is to assume that the things that matter most for predicting the label for a test case are the things that are closest to it. Okay, so you find nearest neighbors, you train a model. But what this ignores is kind of the joint distribution of the label, the nearest set, or the most relevant set. So what we'd like to do is actually take a data point and map it to its most useful neighborhood as a whole. Okay? And that neighborhood may not be the things that are closest to it in feature space. So we've posed this in our work at NIPS last year as a large-scale multi-label classification problem, where during training I have a training image and an indicator vector specifying what the perfect neighborhood would be. And this we found empirically. So we're saying, for this guy, a training set composed of every image in the training set for which there's a 1 would be best or most correct and confident. Do this for all your training images. And now, since this is a very high dimensional space, it's as big as many labeled images you have, maybe millions of them, then what we do is we use a compressed sensing technique to build a compressed label space. So basically some random projection of these very high dimensional indicator vectors into this a compressed label space. Then we learn regression functions that will allow you to map image features to these compressed labels, which are lower in dimension, such that now when you come in with a test image, you can apply those regression functions, get yourself to the compressed label space, and use standard compressed sensing techniques to reconstruct back into the full, very large multi-label classification space. Okay? So all this, what this machinery is an efficient way to allow us to extrapolate or to predict for a new image what is the neighborhood I ought to be using to do training. Okay? So this is a new way to look at local learning where you don't assume nearest neighbors are the answer. It's going to be a combination of neighborliness, and also what's learned about what makes a good neighborhood for a given test point. And we can show again that this helps our results across the board for some important attribute cases. All right, so just conclude, attribute learning is more nuanced than object learning. That's my claim. And we're seeing that it is more challenging to learn a language-true version of an attribute model than perhaps it is for object models. And so it's really essential that we look at ways that the language and the visual concepts can be aligned. And I showed you a glimpse of 3 different ways we've been trying to do this recently. With that, I'll conclude, and thanks for your attention.